In this lab, we're going to be looking at levers, which are a simple machine that can be very simple or not so simple. We're going to look at kind of the more simple side of levers today, which are usually just some kind of plank, a board, a stick or a rod, pole, something like that, that can pivot on one point where one end moves and the other one moves in a different direction. So we can redirect our force. Now, depending on where we put the things that we are trying to lift and move along the lever, closer to one end or the other, and where we put that pivot point can change how easy or hard it is to make that object move and how much force you have to put in to get the same amount of work out without using the lever. Okay, so this is the kind of lever we're going to be working with today. Just the simple one that has three main components. You're going to have a fulcrum, which is where you make the lever pivot upon. So where I'm holding the lever right now and where it pivots on is the fulcrum right now. We have the load or the resistance, which are both ways to say what we're trying to move, what's resisting motion, and what we're trying to change into motion. The thing that has some load we have to lift or change its direction, move it somewhere like that. Okay, usually this comes in the form of a weight, or it can be other things too. But that's what we're going to be doing in this lab, is using weights like this. Okay, the third part is where you put in your effort. Okay, so whether you are pushing up on the lever or pushing down, or whether you are pulling up or down, we need to be applying a force somewhere to try and get the other thing to move. If we don't put some force in, the lever can't do really the work for us, unless you've got like a really nice lever, which whole nother thing. So levers can come in some more sophisticated forms, even though they don't really look like levers. One example is the wheel, or this is a gear, which is a fancier wheel. Okay? A gear still has the same three components that our simple lever does, and so does the regular wheel without all the fancy teeth on the outside. Remember, we need fulcrum, load, or resistance, and where we put the effort. On a wheel or a gear like this, we still have the fulcrum in the middle that everything pivots on. As I apply effort to one side, I can move the load somewhere else. Okay? So let's see if I can hang this on here. It's going to fit. Ooh, it might be too heavy for my board. Okay. Well, I'm not going to actually let it hang because it's going to fall off. The magnet's not strong enough. But you can imagine if I were to put effort here, it would turn the gear. It would move my weight upwards. And if I were to turn it this way and move it that way. Okay, so I can change the direction and the force it takes to move an object, because all these things, these little spikes or whatever, or what would you call them on a bike wheel? Spokes, that's what I was looking for, are coming out from this center point. Now on a wheel, we don't really call it a fulcrum, we call it an axle, but it still does the same thing. That's what it really is. The axle is just the fulcrum for a wheel. Okay, so if you want to get a little fancier than that, you can also have a pulley. A pulley is just a set of wheels, like these guys, that can rotate, okay? But specifically, we use them to move, usually rope, cable, string, chain, through these wheels to reduce some friction, to help something move, be lifted or pulled, which is why we call it a pulley, okay? So in this setup of pulleys, I've got some ropes down here that are running through these wheels, and I've also got some wheels up here on the top. Okay, so if I pull down on this rope here, it redirects the force to pull it up. Okay, you'll notice that out of these two ropes, they don't really move at the same speed. This guy moves a little faster. This guy moves a little slower. Okay, based on how the rope winds around these wheels and how I pull the rope through them, divvies up the force. So I don't have to put in as much force to lift a heavier object. Okay. This should take less force than me actually just picking the jug up and moving it with my own hands. Okay? Now, not every lever or wheel or pulley is made to end up reducing the amount of force that you need to put in to get an object to move. Okay? If you want to figure out what kind of lever you're dealing with and whether it is helping you or making it harder on you, for better or for worse, if it makes the job a longer or shorter distance to get the object to move, or whether it takes a longer or shorter amount of time, the quick way to summarize all that information is the mechanical advantage. The mechanical advantage is just a ratio of your force out divided by your force in. In other words, how much force you'd normally have to output to make an object move, like say lift something upwards, compared to how well your lever can do it for you, okay? Whether it is a simple lever or a wheel or a pulley. Okay, so in this lab, we're going to use different variations on the lever with the meter stick. All we need is some binder clips to clip on here to put our fulcrum, our load, and our effort in certain spots. Then we're going to test out how that changes the force we have to put in to lift an object like this. Okay, regardless of how we set up the lever, the force output it takes to lift this guy is going to be the same. As long as gravity is still the same on Earth and nothing weird happens, it should always take the same amount of force to lift this guy straight up. Okay, what's going to be different is how much easier or harder the lever makes it depending on where we put that load, that weight, where it is compared to the fulcrum, and where we put our effort in. Okay, let's make some levers. So I've got my meter stick. This is what I'm going to use to make my lever out of. I've got some binder clips that I can use to put the location of my fulcrum or my load, or if you want to call it the resistance, okay, and where you want to put your effort. Snap that on there. Cool. Okay, once you've got your binder clips on your meter stick, you can flip them up or down, so that way if something needs to hang from them, like your load, okay, you can have it hanging like that, or if you need to have something pulling up on your lever, like say your fulcrum, where you're going to balance your lever, okay, you can have the clip up like this, okay, so you don't need to flip it over to the other side and clip it on the other side to get it to work. You can just flip which way the clips are going, which is kind of nice. Okay. The lab's going to tell you which places to position your clips, whether they are at one end or another, as well as what we're going to put on each of those clips. Okay, you may have the same position of these three clips. Right now I've got mine at about 50 centimeters for one of them. I've got one about 10 centimeters and one about 90 centimeters. Okay, but maybe one of these times I put the fulcrum in the middle, I put the load over here, and I put my effort over here. Or maybe I put the fulcrum over here, I put my load somewhere else. So let's see a couple different ways I can hook this up. Okay, I've got a pencil that I'm going to put through this binder clip. I like the ones that have this kind of hexagon shape to it instead of like the rounded ones because they don't slide around as much in the clip. Okay, so I'm putting my fulcrum through the top, so that way this is going to be my pivot point where I can make my lever rotate. Hopefully it doesn't do a full circle, but it's kind of fun. Okay, I'm going to set this down on a stack of books, actually make these textbooks useful for something, such that the pencil rests across them. There I've got my pivot point where I can make one end of the lever go up or down. Okay, like so. All right, I'm going to put my load somewhere, my weight, so I'm going to put that over on this side. So I'm going to flip the clips down, hook that on there, set that there. Okay, and then I can apply my effort to this last place where the clip is, okay, where I can push down here to lift the other side. Okay, now to be quantitative about this, to actually measure how much force we're putting in here, I'm going to use a spring scale. Okay, your spring scale measures your force in newtons by how much you pull on this spring, which means if I usually have to push on the lever to get it to work, I'm going to have to kind of flip this the opposite way to do it. Okay, it also means you're going to have to get crafty sometimes. If I try and hook this here, there's not really a whole lot of room I have to make this go down. So what I'm going to do is I'm going to reposition this a little bit. I'm going to put this a little bit farther back this way. So that way, oops, my spring scale can hang off the table so I can pull this thing down a lot more. Okay? Otherwise, I might not be able to see the full strength that it takes, the full force it takes to make my weight move on the other side of my lever. Okay? Now, I've got all this room down here to move this guy, okay, to make this side lift up. So I'm going to start by showing how I can pull down on this side, and then I'll turn it around so you can see on the other side what it looks like to have the spring scale to go down. Okay, so hook this on here. Okay, I'm going to pull this downwards. That's coming out at about 4 newtons. All right, cool. And let me flip it so that way you can see what it looks like on the other side. This time I'm going to put the weight over on this side. So it's going to be kind of hard to see behind the books. But now I can hook my spring scale over here. You can see now that this is off the table, I can pull this down and lift the weight up. Okay, then I can read my spring scale here. If I was stuck trying to do this over the table, there's nowhere really I could put the spring scale to pull down enough to get an accurate measurement. Okay, so instead, I hook this here. I make sure I'm looking at the right side, the one with the N for newtons of force. And then I pull down. Okay, I'm getting about 5 newtons of force there, okay, which is probably, sounds a little better than the 4 newtons I got before. Okay, so about 5 newtons of force to lift this guy. Okay, so you might need to adjust your lever a little bit and where you put it on the table to get your spring scale to work well and to lift the other side. Okay, here's another lever setup I can use. I've got the fulcrum down on one end, I've got my weight in the middle, and I'm going to be doing my effort over here. Okay, so let me set this down like so. Okay, so, that doesn't look good. If you have this problem where your fulcrum is moving on you, whether it's getting pushed up out of the way or something like that, or it keeps sliding on you, I would recommend putting an extra set of books on top of your pencil fulcrum to keep it in place. Okay? Even if it doesn't seem like moving on you, it's good practice just to make sure that things don't fall, so your meter stick doesn't twist and break if you're doing something that's putting too much stress on it. It's just generally a good idea to keep your fulcrum in place like this. So now this is going to be kind of funky. If I push down on this side, all I'm doing is pushing up on the fulcrum. The way this is positioned, I'm actually going to move my weight by pulling up the same direction that the weight is going in, which is kind of interesting. Okay, so if I hook my spring scale up to this guy, this is going to be where I'm applying my effort. My fulcrum is down here, and then, whoops, I got caught on the book. Then I'm going to lift up the weight by pulling up here. Okay, so my load is in the middle, in between the fulcrum and where I am applying my effort force. Okay, it looks like my effort is a little less, a little more than 2 newtons, but pretty close to 2 newtons there. Cool. Okay. There's one more way we can kind of arrange a lever where we have the fulcrum and the load on totally opposite sides. Okay. This is going to be similar in the sense that if I push down on the end over here, it's not going to do anything because I'm just trying to lift up the fulcrum at that point. Instead, I have to lift on the other side, but I'm not going to lift on the other side of the load. I'm going to lift before the load over here, okay, where this clip is. Okay. So I'm going to put my spring scale here. I'm going to pull up, here. That's like maxed out, okay? This spring scale is set for 10 newtons. That's 10 newtons. And it hits the bottom, and then I pick it up, okay? So this is really not making my life easier. If anything, it's making it harder. Okay? Normally, this mass is 500 grams, so it takes about, oops, put that on there, 5 newtons to lift normally, okay? So if it uses 10 newtons to lift using my lever, then the mechanical advantage is going to be something like 1/2, okay, which means it's going to be twice as hard to lift it using the lever. Okay. Now this does have its advantages. If you are willing to put in the extra force, this kind of lever can make things go a little faster, or you might cover a little less distance in how much you pull or push on the lever. But if your goal is to make things easier on you by reducing the force, this is not the kind of lever for you. It's still a lever. It's got the fulcrum, it's got the load, it's got where you put your effort. It just is not prioritized to make the job easier on you. Okay, so in this lab, we're going to calculate the mechanical advantage of different arrangements of levers by putting our fulcrum, our load, and our effort in different places, measuring the force of how much it normally takes to lift our load compared to how much it takes using the lever. And we're going to change where we put these clips as well, not just which one has which thing, but also where we put them along the meter stick. Sometimes you might need to switch your spring scale based on what you're trying to lift. These Brown spring scales are meant to max out at 10 newtons. So we're not going to use anything bigger than one of these 500 gram weights, because this spring scale can lift it with about half that scale. If we do it with this, it's gonna max out, okay? And now that's fine, it's hit the limit, but it hasn't gone past it. But if we use a lever that requires more force than this, then it is gonna max out and hurt the scale. So we're gonna use something that is quite a bit lighter, so that way we have plenty of wiggle room if our lever requires more force, if it has a mechanical advantage lower than 1, less than 1. But keep in mind, if you're using a lighter weight, it might be harder to read the force on the Brown scales, which are meant for greater amounts of force. So if you're having trouble kind of discerning what the force is going to be on one of these scales, especially if you're using a smaller mass, you might switch over to a green mass, green spring scale, which are meant to read up to 5 newtons instead of 10. This is also really good if you have a very efficient lever and you can't really pick between how much force you're actually using with the Brown spring scales, because you really don't need that much.